Welcome to This Explainer. Today, we are pointing our focus toward what I think is easily one of the most mesmerizing structures in our entire solar system, Saturn's rings. But listen, we aren't just going to look at them as pretty, static bands of ice and dust. No way. We're going to explore Saturn for what it really is, a humming, highly active, and frankly, chaotic laboratory of planetary physics. Over the next few minutes, we're going to decode the complex hidden mathematical choreography that dictates exactly how these rings behave, shift, and somehow survive.
Okay, let's dive right into this. I want you to picture Saturn's F ring. If you look at the raw images we got back from the Cassini mission, this specific ring looks like a totally tangled, braided, knotty mess. It's got these weird channels, bright clumps, and episodic jets that just seem to pop out of nowhere. Now, you might look at that and think, well, that's just random space debris smashing together, right? It's just stochastic, chaotic meteoroid impacts. But is it really just a random accident? To answer that, we have to zoom out and understand the massive, super dynamic system that this ring lives inside.
Saturn isn't just a planet. It's an environment of absolutely incredible extremes. And the rings are caught right in the crossfire. We're talking about a vast system stretching all the way from the inner D ring out past the expansive E ring, and even reaching the incredibly distant, faint Phoebe ring. It's a domain completely dominated by a ridiculously powerful magnetosphere and populated by dozens of moons. And these moons span total geologic extremes. You've got Titan, with its dense, smoggy atmosphere, and then you have the icy, fractured plains of Enceladus. Add in active weather and long-term seasonal variability, and you get an environment that is continually reshaping itself. Understanding this restless system is absolutely crucial to grasping why these ring dynamics matter.
To truly understand what's going on here, we have to look deep inside the planet itself. But obviously, we can't just peer into Saturn's core. So what do scientists do? They literally use the rings themselves as a giant, incredibly sensitive seismograph. It's a field called chronoseismology, which is just a fantastic word. By tracking very specific features in the rings, like certain waves in the C-ring that aren't caused by any known satellite orbits, scientists can map out the planet's gravity fields. This gives us a direct window into Saturn's three-layer interior structure. The rings are quite literally vibrating in tune with the planet's internal architecture. But the planet itself isn't the only thing pulling the strings here.
The moons are also incredibly active participants in this cosmic dance. Take Enceladus, for example. Beneath its icy crust, you have this coupled freezing and vaporization of liquid water that feeds roughly 100 distinct jets and curtain eruptions right along its surface tiger stripes. This material blasts violently into space, creating a massive plume. Just think about the scale for a second. We go from microscopic ice grains erupting from the surface to a massive plume that extends for thousands of kilometers. And those tiny grains don't just vanish into the void. They get scooped up by Saturn's magnetosphere, and they literally form the expansive E-ring. The moons are actively feeding the ring system.
But here's where it gets even cooler, because these moons have this fascinating duality to them. While a moon like Enceladus injects material to feed the rings, other moons act like giant cosmic sweepers. Take Janus and Mimas. Saturn has these gigantic proton radiation belts that reach hundreds of thousands of kilometers out into space. Because moons like Janus and Mimas orbit right inside these belts, they act as solid boundary walls. Whenever high-energy protons try to diffuse inward, bam, they crash right into these moons and are completely absorbed. So the moons literally carve out isolated, safe zones in the radiation belts. They give material and they sweep it away.
This delicate balance of giving and taking, of pulling things apart and pulling things together, reaches its absolute extreme at a very specific boundary known as the Roche limit. This is the precise distance where a literal tug-of-war is happening 24/7. On one side, you have the immense tidal disruption of Saturn's gravity just trying to tear everything to shreds. On the other side, you have this self-gravity and collisional sticking of the ring particles desperately fighting to clump things together. Sitting right here, precisely on this razor's edge of stability, is our tangled, chaotic-looking F ring. It's basically the ultimate proving ground for aggregation versus fragmentation.
Now, the F ring doesn't just sit there in isolation. It is constantly being bullied by two specific shepherd moons. First up, we have our primary driver, Prometheus, which interacts with the ring on a 112-orbit recurrence. Prometheus aggressively dives in, carving out these deep channels and triggering the formation of really dense knots and streamers. Then we have our secondary modulator, Pandora, orbiting just outside the F ring. It operates on a 71-orbit synodic period.
It provides a weaker but absolutely crucial pull on the outer edge. This dual moon forcing is exactly what sets the stage for the incredibly complex physics happening down at the micro level.
So the crucial point is, how does this material actually clump together under all this intense gravitational stress? This is where we get into a really cool physics regime known as nonlinear mass aggregation. In the mathematical model, this is represented by the very elegant term K times m to the power of n. Here, K represents the overall efficiency of the clumping, and m is the mass. But the real magic, that's the exponent n. When n is greater than 1, we aren't just seeing simple linear addition. This is driven by self-gravity and a phenomenon called shear reversal. Because the particles are moving at different orbital velocities across the width of the ring, they constantly sweep past one another. At a certain mass, the clump's gravity dominates over the shearing force, allowing it to capture additional material superlinearly.
Think of it like a snowball rolling down a hill, but on a massive cosmic scale. First, small micron to meter-sized aggregates bump into each other and stick. But because of that exponent n being greater than 1, the growth doesn't just chug along at a steady pace, it accelerates into a runaway gravitational collapse. The larger the clump gets, the greater its collision cross-section and self-gravity become, meaning it sweeps up new material exponentially faster. It captures material faster and faster until, boom, you hit a tipping point, triggering a massive avalanche-like clumping event. This positive feedback loop is exactly what creates those brilliant, dense knots that the Cassini spacecraft photographed.
But as you might guess, these giant clumps can't just grow forever. They are constantly fighting the sheer violence of their own environment. And there is a hard limit. The absolute sticking threshold is exactly 1.78 meters per second. If the relative velocity of these massive aggregates exceeds this highly specific speed, the collision no longer builds the clump up, it completely shatters it. The fragments are violently dispersed right back into the ring. So the F-ring is locked in this endless rapid-fire cycle of superlinear aggregation followed by explosive fragmentation, all timed perfectly by the gravitational metronome of Prometheus and Pandora.
And this brilliantly illustrates exactly what that math looks like when things get chaotic. When we crank up that aggregation efficiency, the math perfectly reflects the physical chaos we see in the images. Look at this phase space plot where the exponent n is dialed up to 1.30 and the efficiency k is 0.62. Notice those thick, non-elliptic loops with massive radial excursions? What this tells us mathematically is that the system has entered a highly modulated, completely chaotic regime. The waveforms get distorted, you get these sharp pulses, and the ring experiences intense, intermittent phase slips. It's a complex, sideband-rich mess of behavior.
Let's move on and see how this builds when we isolate the dynamics. By mapping this onto a unit circle using stroboscopic sampling, we can directly look at the angular organization. When the exponent n is at 1.28, you see this wonderfully thin, orderly circle. That means the ring is experiencing stable, smooth, quasi-periodic motion. Everything is behaving nicely. But as you increase that nonlinearity parameter just a bit, that nice thin line completely broadens into thick, fuzzy, chaotic bands. Push it even further, and the solutions break down entirely into these dead zones.
Now this is absolutely wild. What is truly mind-blowing about this nonlinear mass aggregation regime is its extreme sensitivity. A shift in that n exponent from 1.28 to 1.30 is a mere 1.5% variation. That's practically nothing. Yet that microscopic tweak near a critical stability boundary fundamentally rewrites the entire dynamics of the F-ring. It takes the system from a balanced, smooth, predictable oscillation straight into a state of wild, unpredictable modulation. It perfectly proves that this ring is operating right on the absolute razor's edge of a critical threshold.
So what does this all mean for us? What's the grand takeaway? Well, the apparent chaos of Saturn's F-ring, the braids, the clumps, those sudden violent jets, it is not the result of random stochastic meteoroid impacts. Actually, scratch that. It's the exact opposite. It is a highly tuned, deeply deterministic system. The complex morphology we're seeing emerges directly from the multi-frequency dynamics of Prometheus and Pandora interacting with the nonlinear mass aggregation of those tiny ice particles. It's a self-sustained oscillation. It breathes in and out, building up and shattering apart, and it is resilient precisely because it operates near this incredibly delicate boundary of stability.
Which leaves us with a truly staggering thought to wrap up on. We have just taken one of the most chaotic-looking structures in our entire solar system and revealed the elegant, deterministic mathematical engine that's actually driving it.
And here's the thing, this exact framework of driven granular systems and multi-frequency resonance doesn't just apply to Saturn. If the seemingly chaotic F-ring is actually a finely tuned dance, what hidden mathematical order is dictating planetary formation, accretion disks, and the rest of the cosmos? The next time you look up at the night sky, you might just see the math weaving it all together. Thanks so much for joining me on this explainer. I'll catch you next time.